Make okay. Good afternoon. Okay, first I will give a brief introduction about the Professor Professor Shiraishi. And Professor Shiraishi is now a professor at Department of Electronics Science and Engineering, Kyoto University. He has published over 150 technical articles in peer-reviewed journals, including book chapters and review articles, and have given more than 50 invited presentations at the international conference. He received the Outstanding Research Award of the Magnetic Society of Japan in 2013, and the Commendation Award for Science and Technology by the Minister of Education, Culture, Sports, and Science and Technology in 2017, and the 36th Osaka Science Award in 2018. Okay, let's welcome Professor Shiraishi. Give us a talk on spins in low-dimensional material systems, transport, gate control, and conversion. Professor Shiraishi, now time is yours.
Okay, thank you very much, Professor Chen. First, I would like to thank you very much for your kind invitation for this talk, and also thank all of the audience for joining my talk. So as introduced, the title of my talk is Spins in Low-Dimensional Material Systems, Transport, Gate Modulation, and Conversion. And in the first part of my talk, I introduced the significance and attractiveness of such low-dimensional material systems in Spintronics. And in the second part, please allow me to introduce my own works related with this topic. So, but before starting my talk, please give me 1 minute for the advertisement of the activity of my IEEE Magnetic Society. Actually, Magnetic Society strongly told me not to skip slide, and this is the most important slide in my talk, I can say. So the Magnetic Society is one society of IEEE, and now 3,000 regular and student members. So the society organizes some international conferences, Intermag, MMM, TMRC, and so on. As you may know, in the next June, Intermag MMM joint conference is held in New Orleans, hopefully in person. And we always welcome people to give their presentations about their cutting-edge research activities. And every year, usually, the society organizes a free summer school for graduate school students. Actually, last year, the school was planned to be held in Taiwan, but it was canceled. And this year, no plan, of course, due to the COVID incident. So, but in near future, we are hoping to come together in some places for the summer school. And IEEE Fellow nomination is also important activity, and my own distinguished lecturer program. This is also very important activity of the society. The society publishes some scientific journals. Some of you may know. So IEEE transactions on magnetics and magnetics letters. And we welcome you submitting your nice results to these papers. And of course, please join the IEEE and the Magnetic Society if you are interested in these activities. Okay, so I finished the most explanation of the most important slide. I can be more relaxed. And let's move on to the scientific part. So as you may know, spintronics is the field of control spin degree of freedom in solids, mainly, sometimes in liquids, but mainly in solids. In the first generation, metallic spintronics attracted many people, and GMR, TMR, these outstanding discoveries were reported by Albert Feld, Peter Greenberg, Jagadish Mudera, Terunobu Miyazaki, and so on. In the second generation, semiconductor spintronics is a new rising star, and diluted magnetic semiconductors and spin transport in inorganic semiconductors. These topics attracted many people. Now we're in the third generation, I can say, and spin currentronics and spin orbitronics. These are main topics in the latest age of the spintronics. And spintronics has a fundamental physics side and application-oriented side. And I'm the guy of fundamental physics. I myself much interested in physics of spin current and physics of topology, where spin momentum locking can be realized, and spin currentronics, which is a fusion domain of spin currentronics and thermoelectronics. However, of course, I should say that importance of application side of spintronics is also very, very important. And because green IT or novel IT, these new IT systems can be established by the progress of the spintronics. So in both fundamental physics and application physics, transport and control and conversion of spin degree of freedom, they are very important. So for example, to realize spin transport in solids, many experimental approaches were established. For instance, electrical spin accumulation method, a dynamical spin pumping method, and so on. So to control spins propagating in solids, in the first and second generation, we have been using solid gating and external magnetic field to control spins. However, in the third generation, more sophisticated methods are established. For instance, ionic rigid gating or SOI proximity. So conversion of spin is very important because spin is not a conserved physical quantity. And because of this reason, we need to convert spin degrees of freedom to the other physical quantity, which are conserved one. And to realize the spin conversion, potentiometric method or inverse spin Hall effect, where SOI plays a very important role. So these methods are established. So here in this slide, I show the materials chronicles in spintronics. In the first generation, people focused on the metallic materials, for instance, copper, aluminum, and silver. And along the spin orbitronics direction in the third generation, so heavy metals becomes much important. Here, I mean the heavy metals to be platinum, tungsten, bismuth, and so on, because they have a sizable SOI, which allows efficient spin conversion. Along the spin currentronics direction, in the second generation, silicon germanium, these group for inorganic semiconductors, and the 3-5 compound semiconductors, they are very important materials platforms. And but more recently, in the third generation, graphene, TMDs, these kinds of atomically flat materials becomes much important. And heterointerface system, which can be formed in the oxide 2-degs or topological insulators, they are also becoming more important in 21st century. And if I can be more brave, ultrasymmetric materials. This is also very important new low-dimensional material system in modern spintronics. So as I mentioned, they are all low-dimensional material systems. So here now you can understand the importance of these material systems in modern spintronics. At the same time, these low-dimensional material systems plays a very important role in spin orbitonics. So here I show some examples, TMDs, topological insulators, and this is our latest result. But even in silicon, emergent Lashbar field can be created, and this can control the spin degrees of freedom that propagates in silicon. So in this sense, in third generation of spintronics, these low dimensional material systems are the pivotal materials platforms to explore new physics and for creating new types of spin devices. So this is a brief summary of the introductory part. And in the conventional spin currentronics and spin orbitronics, I mean the first half of the third generation of spintronics, bulky materials have been playing an important role. However, in the modern spin currentronics and spin orbitronics, I mean the cutting edge of modern spintronics, these low dimensional material systems playing the central role. At the same time, I should emphasize that the pioneering these attractive low dimensional material systems can open the new pathway for the further progress of future spintronics. Sorry. Okay, so from here on, I introduce some milestone works using low dimensional material systems. So first example is, of course, atomically flat materials, because they are originally two-dimensional materials. The first important material is graphene, of course. And in 2007, a group of Groningen in Holland reported the first spin transport in single-layer graphene at room temperature. And this opens the frontier of graphene spintronics. So my group was also interested in this material. And in 2016, we reported the very efficient spin conversion, unbipolar spin conversion in single layer graphene. And I briefly introduce this topic later. The second important material is transition metal dichalcogenized TMDs, because spin polarized varytronics can be established by using these material systems. In fact, Kim Fai-Mak and co-workers reported the polarized light emission from the single layer MOS2 molybdenum disulfide monolayer by using the spin polarized vary state. Soon after that, group of University of Tokyo reported the reciprocal effect. Namely, they injected the circularly polarized light to the single layer MOS2 and observed the vary dependent Hall effect. So my group was, I myself was a little bit hesitating to enter this TMD role, but luckily I was able to work with an excellent Indian postdoc, and he established the formation of low Schottky barrier height system between single layer TMD and ferromagnetic metal. So here, ferromagnetic metal is perpendicular to the PMA or in plane both. So now we are doing some interesting works using TMDs by combining with various types of ferromagnetic electrodes. So, but I should emphasize that the other type of new material platform, namely the van der Waals heterostructure. So here I show some important works, and as you see, here they use the heterostructure between single layer graphene and TMDs. And because the proximity in this spin-orbit interaction is created in graphene from TMD, and because of this, spin lifetime perpendicular to the graphene plane is much longer than that along the in-plane direction. And also the proximity in this SOI allows the observation of spin Hall effect, inverse spin Hall effect, spin galvanic effects, and now this van der Waals heterostructure is a good material stage for spin currentronics and spin orbitronics. So the second important material systems, low dimensional material systems, is Rushbar splitting system in heterostructure. The pioneering work was carried out by Christian Nass and co-workers in Stuttgart. And they fabricated bismuth silver alloys. And in that material systems, they observed the gigantic rush bar spreading. So this table shows a comparison of the rush bar parameter alpha R, and you can see bismuth silver possesses gigantic rush bar splitting. Because large rush bar field is, we can realize the efficient spin conversion at the interface between such material systems. And this was originally proposed by Edelstein from the theoretical viewpoint. And this is a very small, simple paper, but the contents of this paper is very, very fruitful. And he theoretically proposed the possibility of the efficient spin conversion in this system. And in fact, group of France, headed by Albert Feld, firstly reported the efficient spin conversion by using bismuth silver system, because such kinds of rush bar splitting is existing at the interface. And this cartoon shows their device structure, and they fabricated bismuth silver bilayer, and alloy is equipped on top of silver. So under spin pumping condition, spin current is injected from permalloy into silver, and the spin current is passing through the silver and reach as the interface between silver and bismuth. And thanks to the large bar splitting, the spin current is converted to the charge current, resulting in the detection of the electromotive force. And my group was also doing the similar work by choosing the EEG as a spin source. And also we can control the stacking direction of bismuth and silver, which allows a more precise estimation of the spin conversion efficiency. The second important system in rush bar splitting is, of course, as topological initiator. So now some of the audience wonder if what is heterostructure here? Here I emphasize that this is heterostructure is a topological material and vacuum, because Chan number, namely the vary phase of topological initiator and vacuum, are not continuous. And because of the discontinuity of the vary phase, so twisting of the wave function takes place that allows such kinds of spin polarized Dirac-like linear band at the surface of the topological initiator. And the spin momentum locking, it can be induced by this unique band structure as shown here. And this is the reason why many people, millions of people are attracted by this material. Just a moment. Yeah, as I mentioned, vary phase is a very important concept to determine the topological nature in solids. And but the vary phase itself appears in many different situations. So I show some examples here. For instance, spins in magnetic field in a adiabatic closure, and photons in glass fibers, and quantum hole system, spin hole system, and topological initiator system. So in this sense, now this is one of the hottest research topic in solid state physics. And my group tried to detect the surface spin polarization due to the spin momentum locking in 2014. And at that time we used the bismuth antimony tellurium selenide, which is a three-dimensional topological initiator, particle initiative, and we successfully detected the resistance hysteresis of the which comes from the surface spin polarization of the 3D topological initiators. And my group is also interested in the other type of topological material, and here I show one example. So here we reported the gigantic spin hole effect, spin conversion. So by using the cobalt to manganese gallium, so while ferromagnet. In that work, we used the CMZ as a spin source and spin detector, and by fabricating such kinds of non-local spin bulb device. And spin current is generated from one CMZ electrode, and pure spin current transports in copper wire and reaches at the detector CMZ electrode. Thanks to the topological effect in CMZ, absorbed spin current is efficiently converted to the charge current, yielding the electromotive force. And we observe the spin Hall and inverse spin Hall signals, and we clarify the breaking of the orthogonal reciprocity in this material. And also we quantitatively estimate the spin Hall angle of CMZ to be minus 90%, very large value. The third example is a 2D system. 2D means a two-dimensional electron gas. And the famous system is lanthanum aluminate, strontium titanate bilayer, and a two-dimensional electron gas can be formed at the interface of these two insulating oxides. Both are insulating, but 2D is formed at the interface because the dielectric constant of strontium titanate is quite large at low temperature. And this allows the strong Rashba field formation, and this allows the creation of 2D system. Here the point is that strontium titanate is insulating. We can apply the gate electric field to the 2D system. And as I previously explained, the spin conversion can be realized by the large Rashba field. And in addition, the spin conversion is gate tunable. And the group of France nicely demonstrated the gate tunable spin conversion in oxide 2D. So my group also used this system, but for the other purpose, namely spin transport. So as I mentioned, dielectric constant of strontium titanate is quite large at low temperature, but the value largely decreases at room temperature. This means the Rashba field in the 2D system is becoming very weak. In such a case, spin transport can be realized. This is what we expected. And we fabricate such kinds of spin transport device where we use the spin pumping technique, and the spin current is injected into 2D, and this propagates in the 2D and adsorbed in the separated non-magnetic electrodes, which have a sizable spin-orbit interaction. And we detect the electromotive force by the inverse spin Hall effect by the injected spin current. So by measuring the output signal as a function of the gap length, we estimated the spin diffusion length of in this oxide 2D to be 300 nanometer at room temperature. The detail is described in this paper published in 2017. Of course, gallium arsenide-based 2D is the other important material systems for Spintronics, and a group of Regensburg intensively studied these material systems, and they reported the successful spin transport up to 50K, and also they reported unexpected enhancement of the spin signals due to the resonance tunneling effect. So the other important achievement is the formation of persistent spin helix state in these material systems, which was reported by a Japanese group. And as shown here, we can control the Rashba and Dresden-Haus type spin orbit interaction by changing the crystal directions and also bias voltages, and persistent spin helix state where spins do not dissipate can be realized. So the final example is the ultrasymmetric film. So of course, platinum is a metallic material, but when we fabricate very thin platinum, we can control the resistance of the metallic film by the gate electric field, and more importantly in Spintronics viewpoint, so we can largely control the inverse spin Hall effect. So later on, I explain the achievement in detail. And also in the second part, I explain the latest results from my group, namely the synthetic Rashba field SOI formation in silicon. Okay, so this is the end of the first part. And from here on, I explain some results from my group using low dimensional material systems. So in today's talk, I focus on the gate modulation of spin orbital interaction in platinum and silicon. So here in this slide, I summarize what the spin orbital interaction is. Although all of you understand the physics of SOI very well. So spin orbital interaction is a coupling between the spin and orbital angular momenta. And coupling strength is roughly proportional to the force power of Z. Z is the atomic number. So here I emphasize that this is holds under very rough estimation. So in fact, theoreticians carried out the calculation of the magnitude of the SOI as a function of the atomic numbers. As you can see, of course, in principle, the magnitude becomes larger when the atomic number is increasing, but it depends on the outer shell electrons. But anyway, so we can roughly say the heavier element induces larger spin orbital interaction, namely the efficient spin conversion. The third important thing is that until recently, people believed that SOI, but the magnitude of SOI is material specific, and we cannot control the magnitude of SOI. But our achievements overturns conventional understanding of these things. So the first topic is the tuning of the SOI by ionic gating in ultrasync platinum. So before introducing my own work, so please allow me to give one simple quiz to you. So please consider the situation that when you add the glass of water into C and empty cup. So the question is whether you can recognize the water amount change in both cases. Can you recognize it? Of course, the answer is simple. So when you add a glass of water into C, of course, you do not recognize the change of the total amount of water. If your answer is yes, you are regarded to be full, unfortunately. But if if your answer is no, so this is not scientifically correct because we cannot recognize it, but the total amount itself actually increases. This is a very tricky quiz. So in the case of an empty cup, of course, you can recognize the total amount of water changes. So it's not a difficult question to answer at all. But the important thing here is that this is the operation principle of field effect transistors. As all of you understand well, so we cannot fabricate the field effect transistor by using a metallic material. So in every undergraduate solid-state physics textbook, we can find this description. Because metallic materials include a number of carriers. Carrier density is very, very high. So this, in such a situation, even though we apply the very strong gate voltages, which allows the very large carrier accumulation to the system, so we cannot control, we cannot increase the conductivity of the whole system. So this is the reason why we cannot fabricate field effect transistors by using metallic materials. However, we can fabricate the transistors when we use the semiconducting materials because we can control the carrier density, and at the same time we can suppress the carrier density in it. And in such a case, when we apply the strong gate voltages yielding the dense carrier accumulation to the system, we can largely control the conductivity of semiconductors by the gating, and this allows the large on-off ratio of the system. So here my question or my curiosity was on what happens when we fabricate a very ultrasymmetric material with low carrier density. And what happens if we apply the effective gate electric field that allows dense carrier accumulation to the system? This sounds a very stupid question, but that was our motivation. So interestingly, the similar idea was also proposed by the group of Teruo Ono of Kyoto, Teruo Ono's group in Kyoto. And they fabricated the ultra-thin cobalt film, ferromagnetic film. And they also equipped the hafnium dioxide gate insulator on top of the ultra-thin cobalt film. And they tried to control the Curie temperature. The first important thing here is the Curie temperature of ultra-thin cobalt is very, very low comparing with the bulk Curie temperature. But more importantly and surprisingly, the Curie temperature of ultra-thin cobalt is modulated by the gating. So this means gating allows modulation of magnetic properties. And soon after that, soon after that, the same group reported the much more efficient magnetization control by the gating by using the ionic liquid gating technique. So here in this slide, I explain the physics of ionic gating. So first we prepare ionic liquid and we attach the ionic liquid on top of the solid. So in ionic liquid, cations and anions are uniformly dispersing. And of course, under zero gate voltages, so nothing happens. However, when, for instance, when we apply the positive gate voltage, so cations are accumulated on the opposite side of the gate electrode. And in consequence, electrons are accumulated on top surface of the adjacent solids. And when we apply the negative gate voltage, the opposite situation takes place. So by using this technique, we can accumulate freely and automatic. We can control the carrier type that is accumulated on the top surface of the solid. And this ionic gating technique is a very potential way to control the physical properties. And in fact, so superconductivity in potassium tantalate was firstly observed by using this technique, and paramagnetic and ferromagnetic transition in indium manganese arsenide was also realized by using this technique. Of course, my group has been using this very potential way to control physical quantity, and this is one example. So in that work, we control the spin conversion in single layer graphene by using ionic gating. Here I show the device structure, and the single layer graphene is transferred on top of the yttrium ion garnet, a ferromagnetic insulator, and ionic liquid is equipped on top of single layer graphene. And by using the spin pumping technique, spin current is injected from E to the single layer graphene. And by applying the gate voltages, we can control the carrier type in the single layer graphene. As shown here, the red region shows the region where the holes are the dominant carriers. And in the blue region is the region where electrons are the dominant carriers. As you know, electrons and holes have opposite carrier polarity, opposite polarity. And thanks to this change of the polarity, we can see the polarity change of the inverse spin hole voltages by applying the gate voltages. And more importantly, by applying, actually we can apply the very strong electric field to the system. We can clarify the spin conversion physics behind of this unbipolar spin conversion. And we clarified that the inverse spin hole effect, not inverse Rashba Ederstein effect dominates the spin conversion in single-layer graphene, even though spatial inversion symmetry breaking along the perpendicular to the plane. So soon after that, a group of Barcelona, Sergio Valenzuela's group published a follow-up study of our crane. And in that work, they reported the no Lashbar effect is existing in single-layer graphene, even though the spatial inversion symmetry is breaking. So they established such kinds of oblique Hanle technique, and by changing the external magnetic field angles, they observe the saturated spin signals, and from this fitting, they can conclude that the spin lifetime anisotropy is not existing. Means I mean the perpendicular to the plane spin lifetime and in plane spin lifetime are the same. So this is compelling evidence of the no Lashbar, built-in Lashbar effect in the single-layer graphene. Okay, so I come back to my story, and my motivation, my purpose is what happens by combining non-magnetic ultrasonic film and ionic gating. So in the beginning, we expected the first resistivity change, and if we would be lucky, small-bit interaction can be controlled by the gating. This is what we expected in the beginning of this work. Sorry. Okay, so this is the experimental concept. And as in the case of singular graphene, we use yttrium ion garnet, and ultrasonic platinum film is evaporated on top of it. And ionic gel gate insulator is equipped on top of ultrasonic platinum, and we apply the gate electric fields via the platinum foils. First, I show the thickness dependence of the resistivity of platinum. So as you see, when the thickness of the platinum goes down, the resistivity of platinum monotonically increases and very, very resistive. So this is due to the grain boundary scattering, surface scattering, and so on. But this behavior can be theoretically fitted by using this fitting function. And from the fitting, we can extract some physical parameters. But the most important parameter here in this work is the carrier density. And in our estimation, carrier density of thin platinum films to be 6 times 10 to the 21st per cubic centimeter. So some of you wondered if the carrier density of platinum is very, very small. So but it's not surprising. So of course, if we start from the conventional Dorude theory, this means 1 free electron per platinum atom. So the carrier density should be 6 times 10 to the 22nd. But according to the band calculation, only 0.41 electrons are existing per 1 atom. And experimentally, this theoretical calculation is supported, and only 0.24 conduction electrons per platinum atom were measured in their experiments. And in their estimation, carrier density is 1.6 times 10 to the 22nd per cubic centimeter. And in our case, 6 times 10 to the 21st, not so large different. So in this sense, we can say this is a reasonable value. Okay, next I show the gate voltage dependence of the resistance of platinum film. So from here on, I focus on only a 2 nanometer thick platinum, the thinnest platinum film. So when we use the 2 nanometer thick platinum, the resistance of the platinum film is largely suppressed when we apply the strong positive gate electric field. Here I show the IV curves as a function of gate voltages, and you can see linear dependence is maintained in every measuring condition. This means we do not control the interface between platinum and the non-magnetic electrodes. but we control the resistivity of platinum itself. So also we can estimate the accumulated carrier density to be 10 to the 14th per square centimeter. Of course, this is a very large value, but at the same time, I emphasize that such kinds of dense carrier accumulation can be routinely achieved by using ionic gating technique. So this is the central result of this work. So gate dependence of the inverse spin hole voltages. As you can see, so the sizable electromotive forces can be observed at 0 and negative gate voltages. But when we, as we increase the positive gate voltages, so the magnitude of the electromotive force monotonically decreases, and finally almost nothing was observed. So this is the first experimental demonstration of the giant modulation of inverse spin hole effect. To understand the physics behind of it, so we focus on the gate dependence of the electric current generated by the inverse spin hole effect. So here I emphasize that the inverse spin hole effect is the effect to generate electric current, not voltages, because spin scattering is the origin of the effect. And the generated electric current is equal to the inverse spin hole voltages over resistance of the film. But here the important is both are gate dependent. So in consequence, the generated electric current is proportional to the product of the spin hole conductivity, spin current density, and this tangent hyperbolic term. So, but in our case, this tangent hyperbolic term can be regarded as unity, and because of this work, so a group of San Sebastian, Spain, reported the conductivity dependence of the spin diffusion length of platinum, and when the platinum is resistive, spin diffusion length is largely suppressed, and in our case, because of this, we neglect this term in our discussion. Next, we plotted the gate dependence of the normalized electric current. Normalized electric current means as shown here. And if the normalized electric current is not gate dependent, this means the spin hole conductivity is not gate dependent because the spin current density is not gate dependent in our experimental schemes. But the reality is not. As you see, the normalized electric current is largely modulated the gate voltages. This means the spin hole conductivity is modulated by the gating. Of course, spin hole conductivity as a function of the resistivity was investigated by the group of by some people, and this is the result. But according to their claim, according to their manuscript, they claim that the spin hole conductivity is almost constant to the resistivity of the film. But if we replot this result to this famous universal relationship between the normal conductivity and spin hole or anomalous hole conductivity, we can understand the following things. So of course, the Spanish group people control the conductivity of their platinum film and within the intrinsic regime. But highly conductive, I mean the low resistive regime. But in our experimental scheme, our platinum is also within the intrinsic regime, but at the opposite border of them. And in the highly resistive border, spin hole conductivity is largely changed as a function of the conductivity. So this this result is the theoretical result of the theoretical calculation carried out by Contani and co-workers. And as you see, Very curvature term becomes dominant in the highly resistive regime, and thanks to this contribution, spin hole conductivity is can be largely modulated as a function of conductivity. In fact, when we replot our experimental results about the spin hole estimation of spin hole conductivity by changing the film thickness, the results can be nicely reproduced by the continuous calculation. And from this result, we can control we can conclude that we control the spin hole conductivity by the gating. So because we use the low conductive platinum, and the platinum film is within the intrinsic spin hole regime. If our scenario is completely correct, the modulation should vanish in thicker platinum because carrier accumulation ratio decreases and the Fermi level shifting becomes smaller because carrier accumulation do not affect the modulation shifting of the Fermi level so much. And as I mentioned, intrinsic spin hole regime is the key to control the spin hole conductivity. And in the intrinsic spin hole regime, interband spin scattering is the key for the spin scattering. This means that the electron density of state around the Fermi level is very important. But if Fermi level shifting does not take place, so the density of states change is very small, and this suppresses the control of spin hole on inverse spin hole effects. In fact, when we increase the thickness of the platinum film, the effect rapidly diminishes, and this is a strong supporting evidence that our understanding is correct. So this is a summary of the first topic. So we controlled the resistivity, inverse spin hole effect, and the spin hole conductivity of ultrasync platinum by using ionic gating technique. After that, we carried out the we carried out some additional experiments by using palladium ultrasync film and copper thin film. As you may know, the bond structure of platinum and palladium are quite similar, and this means the density of states of the d electrons around Fermi level, the distribution of them is very similar. And we can expect a similar effect in ultrasync palladium here. In fact, as you can see, we can control the inverse spin hole effects by the gating in ultrasync palladium. And of course, nothing happens in thin copper film because copper is a weak SOI material, and density of state of d electrons around Fermi level is almost nothing. So we published this result last year, and this is the latest result about the first topic. And as I mentioned, we experimentally demonstrated gate tunable inverse spin hole effect. And spin hole effect is a reciprocal effect of the inverse spin hole effect. And from the onset of reciprocity, we can expect the successful tunable spin hole effect, as in the case of tunable inverse spin hole effect. So to check our concept, we fabricated such kinds of spin transfer torque devices, and ionic gel is once again equipped on top of the ultrasync platinum, and platinum is equipped onto evaporated on top of permalloy. And we observed the gate change of the output DC voltages, and we observed the gate-dependent Gilbert damping constant of permalloy because the spin torque effect is suppressed. More importantly, the tunable spin orbital interaction in platinum allows the suppression of the spin memory loss. So spin memory loss is attributed to the spin orbital interaction in the system. And as you see, the spin flip parameters due to the spin memory loss is quite large in the combination of heavy metals. And for instance, platinum permalloy system, which we have also introduced, the spin memory loss ratio, spin flip parameter is quite large. However, by applying the gate voltages, the spin flip parameter in our platinum permalloy film is suppressed down to 0.14, almost 1/4. This is also the strong evidence that the spin-orbit interaction of platinum is controlled by the gating. So in the rest of time, I briefly introduce our latest result of the tunable SOI in silicon. As you know, silicon is a very light element. The atomic number is only 14, and silicon has a lattice inversion symmetry. From these facts, silicon has a negligibly small SOI inherently. But this holds to the bulky silicon. In the practical devices, we usually the interface is existing, and for instance, in transistor gate insulator is existing. And when we look at this interface, the spatial inversion symmetry is breaking along this direction. So luckily, we have been investigating the spin transport physics in silicon by fabricating silicon spin Mosfets. And we have a sufficient accumulation of the knowledge about the spin transport physics. So our motivation was what happens when we apply the strong gate electric field, sorry, gate electric field to the silicon channel via the SiO2 gate insulator. So we expected the formation of synthetic Lasheva field. So of course, SOI is intrinsically large in heavy elements and compound semiconductors and heterointerfaces, but people usually believe that the SOI is negligibly small in light element system. And of course, in carbon, no Lasheva effect in single layer graphene, as I mentioned before. So, but what happens in silicon? This is our motivation. So when we come back to the similar work using graphene, very interesting feature was found. So as I mentioned, in single layer graphene, no Lasheva effect is, and this induces the isotropic spin relaxation along the in plane and the perpendicular to the plane. So this is very important, please keep in mind. So if no Lasheva effect, spin lifetime is the same along both directions. But experimentally, in bilayer graphene, so spin lifetime is anisotropic. This means a Lasheva field is. So currently, nobody precisely understands the physics, why single layer graphene does not have a Lasheva field, and then why bilayer graphene can induce a Lasheva field. Although only one graphene layer is stacked, additionally stacked to the single layer graphene. But of course, synthetic SOI is induced in single layer graphene by the combination with TMD, I mean van der Waals, VDE, sorry, van der Waals heterostructure. And this is a big mystery and very intriguing research topic, whether the Lasheva field is existing or not in various material systems. So as I mentioned, the existence of the spin lifetime anisotropy is the fingerprint of the synthetic Lasheva fields. So we measured the spin lifetime anisotropy in silicon by changing the gate voltages. As I show here, the theta is an isotropy factor, and when theta is equal to 1, spin lifetime is isotropic, the same. As you see, the value is is quite close to 1 at low gate voltages, but when we apply the large gate voltage, the theta value is almost 0.75 far from 1. This means the large spin lifetime anisotropy takes place under the strong positive gate electric field. So this is a whole data set of the anisotropy factor as a function of gate voltage. And as you see, the anisotropy factor is becoming far from 1 under strong gate voltages. And also the factor is gate tunable. The other important issue is spin lifetime is almost isotropic at a gate voltage of 10 volt. So as you see, at 0 volt, the factor is 0.9, but at 10 volt, the factor is almost 1. This directly means that the built-in synthetic Lashbar field is existing at the interface between silicon and SiO2, and this is suppressed under the gate voltage of 10 volt, and this means the gate tunable. And also we can estimate the Lashbar parameter of the system from the Hanley type spin precision signal, and the Lashbar parameter as a function of gate voltages is as shown here. And magnitude itself is not so large, 10 to the minus 15th electron volt per meter. But at the same time, I emphasize that this magnitude, this value itself is comparable. It's almost the same as that in strained gallium arsenide, the famous large SOI material. Okay, so this is a brief summary of the second topic. So we successfully demonstrated the detection of the synthetic Lashbar field in silicon SiO2. And this means formation of emergent effective magnetic field, and which is supported by the detection of the spin lifetime anisotropy. And also the other important issue is Lashbar, synthetic Lashbar effect is gate tunable. Okay, so this is the last slide of my talk. So all I can say now is it's very simple message. In modern spin current electronics and spin orbitronics, these low-dimensional material systems allows exploring the new physics and the further progress of spintronics and condensed matter physics. So thank you very much for your kind attention.
Okay, now it's open for question. Any question? Yeah, actually, I have one question for the
yes, please.
For the synthetic, okay, artificial SOI, right?
Yeah.
Small coupling.
Yeah.
For this is induced by the external field or is a beauty induced bonding?
Yeah, currently there are two possible interpretation, we believe. The first one is the interface between silicon and SiO2 itself. So because this is a hetero interface, and as in the case of Bismuth silver or the other bilayer systems, the Lashbar field is definitely is, and this induces synthetic Lashbar field, effective magnetic field. This is one interpretation. So the other interpretation is the thickness of silicon channel. So in the talk, I did not tell you the effective thickness of the silicon spin channel, but the spin channel thickness is 80 nanometer. So of course, 80 nanometer is bulky, maybe bulky, but such kinds of thin spin channel may induce some additional effect that allows the formation of synthetic Lashbar effect. So now we are investigating which is dominant mechanism or more plausible mechanism, and I would like to say please wait for a while.
Okay, then one more question, Claudia. Yeah.
Yes. Good morning. I mean, here is morning. I have a question concerning the topological insulator you are investigating.
Yeah.
So in general, you wrote something like bismuth, antimony, tellurium, selenium.
Yeah.
I don't know if you are really investigating a quaternary system Or my question is, what are the difference between the different topological insulator you can use? Is it just a matter of atomic number, or what are the different properties you can expect?
Yeah, that's a very good question. So because of time limitation, I did not explain the detail. So but in that work, we use a BSTS and also bismuth selenide as a control for the control experiments. So the main difference of these materials are the position of the Fermi levels. As I mentioned, in BSTS, Fermi level is located in between bulk conduction and valence bands, but in bismuth selenide, the Fermi level is located in the bulk conduction band. So according to the temperature dependence of the resistivity, our estimation is supported. And more importantly, we can see such kinds of magnetic resistance effect from the quaternary material BSTS. But when we use the bismuth selenide, not bulk insulative material, we do not see any magnetic resistance effect even at low temperature. This means position of the Fermi level is very important because we cannot access, of course, we partly access to the topological state, but when the Fermi level is located in between the bulk band, we can directly access to the topological spin polarized state, and this allows the easy detection of the spin-dependent magnetic resistance effect. So that's a key to observe such kinds of effect. So in this sense, material selection is very important.
Thank you.
So have I answered to your question?
Yes, it's very, very clear. Thank you.
Any more question?
Yeah.
Okay, actually, I'm very okay. You know, the one more question is about this. Okay, silicon induced this. You know, that's why this is very, very okay. Surprised me. Okay, so for the you know, light element can induce this very large rush bar field, right?
Yeah.
So for this rush bar, have you tried to using this one to measure this spin polarization?
I'm sorry.
The spin, okay, have any spin current generated?
Okay.
Only just some static rush bar field. The normal rush bar field is based on current understanding, right? There's some, maybe we generated some spin current.
Yes. So sorry, I do not explain the detail of the experimental setup. So as shown here, we use the spin Mosfet for the experiment. So in the spin Mosfet, so two ion electrodes are equipped on the silicon surface via the MZO tunneling barrier, and we use the non-local four-terminal measurement technique to generate pure spin current in silicon at room temperature. And because spin diffusion takes place in the system, and the analysis becomes much easier, and we apply the perpendicular to the plane external magnetic field to induce the Hanle type spin precession like this. And when we change the angles of the external magnetic field, the saturation spin, saturated amplitude of the spin signal is different. And more importantly, when we change the gate voltages, the magnitude of the saturated spin voltages becomes different, like this. And by plotting the normalized spin signal as a function of the square of the cosine beta, beta is the external magnetic field angle, then we can extract the spin lifetime anisotropy. So this is a measuring technique. So in summary, we create the pure spin current in silicon, and the Hanle type spin precession was measured. These two things are key to detect this effect.
Okay, so any crystal structure dependent?
Yeah, good question. So now we are using silicon 001. So, and this means the channel, direct channel is fabricated along 001 direction. But of course, the Fermi pocket of silicon is not along 001, and in principle, spin lifetime is crystalline direction dependent. But as far as we have investigated, the difference of the spin lifetimes along the different crystal directions is not so large. And at this moment, our answer is yes or no. So it would be different, but not largely different we expected.
Okay. Yeah, I'm clear now.
Yeah, thank you.
Any more questions from the audience? Okay, if there's no more question, okay. Let's thanks Professor Shiraishi. Okay.
Thank you very much.
Wonderful talk.
Thank you.
Very much.
So Professor Chen, so thank you very much for your invitation. So
okay, so if you have a chance, we come.
this is my last talk
yeah.